one good thing of this technique, which is used also in our technology, is that if you are communicating at the same time with two different spreading codes.
Okay. So, guys, I would like to welcome you all to this series of talks that we hold in the postgraduate program. Okay, today we are having Professor Luigi Mancini from La Sapienza, that is the University of Rome, and he's visiting us. We are trying to establish probably future partnerships between UFSC and La Sapienza, and he'll be talking today about this MaleficNet, how to hide malware into deep neural networks using spread spectrum channel coding. Okay, so it was an invitation for him to come, and he offered this talk. I think it will be very interesting for a lot of people, not only for us in security, but also in other areas. I know that some people here that works with intelligent vehicles and these kind of things. It's very important to understand how this kind of malware can get into the way of these kind of solutions. So, Luigi, take your time. And thank you very much for accepting.
My pleasure. Thank you very much for the invitation, Professor Martina, and I in particular like that I can talk to the students here, which is always good because we are the future, right? Now, I'm talking about this technology that we developed in Rome. Was a kind of multidisciplinary work. There were colleagues from the Stanford Research Institute and also colleagues from Zurich, from the Center of Supercomputing in Zurich, because really we put together not only computer science and documentation, but also telecommunication and other technology like this, in order to prove that this is impossible, how strong it is. The result is devastating. It's devastating for all this technology about machine learning. In particular, if you consider today that most of the machine learning models are very expensive to build, so most of the people use models that are already available, no? In GitHub or whatever, right? So you have models that are already trained, and you download this model, then do the fine-tuning and use for your own purpose. Okay. If this model that are already available contains malware, this technique allows to spread this malware inside the model itself, inside the parameter of the model itself. Okay. This is the main idea. The intuition is the following, is that the parameters of the model have a capacity which is, in terms of storing information, which is way bigger than the information that they store in order to perform their function. It's much more, order of magnitude more. So there is space to add other information inside the network itself, like in this case malware. Okay, this is the fact. Okay, before I probably it doesn't interest you, but I tell you I have to tell this before I go into the details of the technology, some statistics about the university I work in. So this is one of the largest university in Europe in terms of enrollment of students. We have 125,000 students enrolled in our undergraduate and master courses. It is, it has research acknowledgement, relevance research acknowledgement. You see, for example, Marie Curie Fellowship, the fellowship that are given in Europe to the best researchers. We have 40 very cheap, but also the ERC counts grant 15, which is 60 million euros. The ERC research counts grant are given to persons which are which perform relevant research at the European level. So it's also one of the oldest universities in Europe. It's about 13th century. So within this university there are a lot of departments, which is about 57 university departments. It covers more or less all the disciplines. It's a generalistic university. We cover all disciplines. One this department is computer science. Okay, there is one department of computer science. I belong to this department. In this department, we run a course in cybersecurity. Okay, there's a master course in cybersecurity, which is in English. So it's only taught in English. We have international students attending this in addition to Italian students. It's a course that is it's a 2 years master degree that is there until since 10 years old. Before there was a master course for 1 year. There was a master course for professionals. So it's kind of continuing education on cybersecurity before that. But now it's a really program structure. Okay. So our department was one to offer a master degree in cybersecurity in Italy. Now let us talk about our work. So I told you more or less what are the motivations. Okay. So there is this threat that the neural network might contain malware, and this is a threat in particular if you consider the supply chain of the neural network, and now consider also machine learning as a service, essentially downloading machine learning. Okay. So what we did is the following step. So it is possible to introduce a malicious payload inside the weight parameters of the neural network. Okay. Weight parameters, are we call it as are the value, usually small value, that are assigned to a neuron, and then they are used to compute all the learning function. Okay. What is possible to do here, what we found out, it is possible to do that. Probably with many techniques, It's not necessarily, this is not the best techniques, but we use the CDMA perspective channel coping because it's a well-studied technique, and there are proof, formal proof, about the resilience, the detectability of the technique, and so on, that we can inherit this in our machine learning framework. This is mainly the reason because we use technique. It's not necessarily the only way to do that, but this is one way to do it. So, what is important here is that, if I want to add a malware in a set of weights, basically a set of numbers, like numbers, I can add a malware, they are changing this number, and this is going to affect the, the accuracy of the model, machine learning model. Now, what is the trick here? The trick is that I want to embed the malware without affecting the accuracy. I want that the network continues to work as if there is no malware. Okay, that's the difficult part. So, One thing that is also important here to consider is that the network that we have now that are available, like for example, JAMA, the one that Stanford University is fundamental nodes. They have billions, sometimes trillions of parameters. So the number of weights we call the weights parameters are billions, trillions. So they are a lot. So if we were changing a little some of these parameters, even 1 billion or 2 billion of these parameters, the accuracy, it's not easy to detect that has been this change, and the accuracy may be affected very little. Right? So that's the point. So the actual models are very big, are very huge. They have trillions of parameters, and this may be something that are possible. Okay. Now, a few words about code division multiple access. So this is an old technique I was saying before, and the idea is what I told you. So basically, instead of sending your communication in one specific signal, you use actually in the original technique you use basically random numbers to multiply to change the frequency you are using. Okay, you are hopping between different frequencies at high speed, and if the adversary know exactly the sequence of your hops, he can reconstruct the message. Otherwise, he cannot. So this is the initial technique, but it has been improved a lot, and this is part of the code division multiple access scheme. We are using this to embed the malware. How? This is for a better expected intuition, but otherwise we're going to use the intuition is the following. If you consider a weight as a frequency, what we do, we spread the malware through millions of weights. Okay? This is basically the idea. Okay? So we use a spreading code. You transform the malware with the spreading code in a sequence of small value, and these small values are added to each of the weights, millions of weights. The spreading code is common to the attacker that is doing the encoding of the malware, and also when you do the code, you use the same spread. Okay? So this is it. Basically, instead of using many frequencies, we're using many weights. Each weight is like a specific channel of communication. Okay, this is the idea. Given that, with what we do, you have a network like this, where each node has a parameter, and we have the malware on the left. And what we do, basically, we are encoding the malware inside this weight, specific weight. So basically, network becomes a storage for the malware. Okay. So I don't want to go too much in this detail, but basically we have a payload. We run a payload which is a given number of bits, which is P capital P, and we call it vector B. So bit 0 to B minus 1. So basically, if I have a malware of 10 megabits, I have a vector of 10 megabits. Okay, so B is a vector of 10 megabits, and I want to encode this inside them. Okay. To do this, I don't go to this solid details because otherwise it becomes too complex. What we do is this. Okay, this is what we do. So W is a matrix, which is the original matrix of the original weights. Okay. Then to this matrix we add what? We add B, which is this vector with malicious code, that we multiply with another matrix C, which is the spreading, what is called the spreading code. Okay. It's a matrix because by the standard, this is what you do. You have to multiply your message for every line of the words. In order to spread this towards the ways to multiply this value. Gamma is a gain factor to control the power of the signal. So we have to control the power of this amount, to give it small, so that it cannot affect the performance, it cannot be detected. Okay? So this is the kind of embedding. Can be other embedding. This is good because you can prove a lot of problems that comes from the communication theory. Okay? One thing that you have to consider that the matrix C can be very large. So consider if this is 10 megabit B and you have 2 billion. This matrix is huge. It's not possible to really to do in practice. So what we did, we make an extension which you consider basically block by block. So you can embed, instead of embedding the whole 1 megabit, you embedding 1 kilobit in a portion of the matrix, just one portion, and then another block in another portion, and so on. Okay, so that you manage to keep this spreading matrix small. Okay. So this is a kind of block-based embedding. Okay. That is an optimization that can make the attack feasible. Okay. Now, this is the way it is recovered. This is the way you recover the malware. This comes from the spelling code theory. Okay, the way it goes. Basically, you have the weights that are already modified. Then you multiply that with the spreading code that you use to embed it. That's transpose. Then you get the number, which is BI, it's called BI. And the sign of this number is the bit. So where plus means 1 and minus 0. Okay. So the sign of the signal is the bit you have to transmit. So this is the way you can do stuff. So it's an extremely reliable way to embed. The original technique is extremely resistant to jamming. It's resistant to the fact that you are disrupting a channel. If you disrupt, a jump of frequencies, still you can reconstruct the signal. Because it's extremely efficient. In addition, in our case, to be even more reliable, robust, we add error correction code, LDPC. So in addition, we add also so that we can even make the embedding very robust. Any question? I have one question. Probably most of you will have this question. So the question is, okay, this is storage.
I may have not understood it perfectly, but I'm still questioning how can this, as the checks and validation, or any kind of checks and validation at the receiving side, because if you're transferring the network, right?
Yeah, well, wait. No, the easiest way to understand is, suppose that is a user that wants to use a model that's already published somewhere, he wants to download it to do fine-tuning to use it, to solve some problem. This is the easiest way to understand. So, in the initial model, we embed malware.
Okay.
Then the victim is downloading the model, believing it is a clean model, while it's not, because it contains malware inside. Okay, so no communication. Okay, just passive. So the model is spread in a way to spread the malware through a machine learning model.
Yeah, the original checksums are incorrect. I see.
The original checksum is already correct. May not be, because now maybe that the original model has been built in this way.
Yeah.
The original model has been built with the malware inside, and then if you want the checksum, there is a checksum of the old model, which is perfect.
Yeah, I see.
Okay.
That's what I meant. Yeah.
Okay. It's not a rush. The original model is perfect. It's the way it is. Of course, you can embed this also in the supply chain of the model. If you don't see a large company, like Facebook, so you can have part of in the construction of the model that is malicious, and they are inserting malware in the model. In the company itself, it is building the model for us. So,
That's not the question. That's already quoted.
that's the question. That's the question. So I explained how embed, how to use a machine learning as a container map. How do you run it? But once you have, there are several ways, there are several options. Right? So the easiest option is suppose that I have this malware the attacker has spread this malware in millions of people on device. He may have an access to this device independent from the malware. Right? So the device can be can have vulnerability smart. For example, I can use this. I can embed this in the App Store. I can build an app, which is a small neural network in it to do some service, and in the neural network I put this malware. So when you download malware in your smartphone may have a different vulnerability. I can do the instruction run. This is way. Another way that we experiment is to use basically there are a lot of attacks in deserialization of machine learning model in the target function. Insecure deserialization. So when you download the model, the library of the runtime support are going to deserialize the model and run. There are ways in which you can do the activation of the malware in this phase. Okay, when you are deserializing the model to run. Okay, this is the second one. But anyway, the major thing is that there is another vector now to bring malware in the system, which is the neural network itself. Now, some evaluation. First of all, I told you that the technique that I'm using allow concurrent communication by construction. So suppose that this paper is already published, so people know that this is technique. So we know that the attacker may use this technique. So one could think, okay, I am embedding in my neural network a noise, random noise, using the same technique, using a different spreading code. So that I'm going to overlap the malicious signal. Well, this is not possible because it's not possible anyway because the spread spectrum is designed to have concurrent communication and there is no interference. So if I'm embedding even 10 megabit of noise in my neural network using a different spreading code, the neural network is going to handle both. We'll keep the malware and we'll keep also the noise in different channels without any interference for the way the coding works. So we have to think about other things. So we have evaluate three dimensions. The stealthiness of the model, meaning that if it can be detected or not. The impact of model performance. How large can be the malware before the model degrades. And the robustness of the malware with respect to the defender that wants to remove it. Okay? Let us see the stealthiness first. Okay? So, we have done two experiments. One using anti-malware software, antivirus, anti-malware software, and the other one doing statistical analysis of the weights to see if there are things that are true. As for anti-malware software, we have this result. So, here we have the malware that have been embedded. Stuxnet, Strover, and so on. They are relatively increasing size. Okay, they are increasing size. So this is the plain malware. So the probability to detect the accuracy, the detection rate of meta defender with this feature if you give the malware flavor. This is the detection rate if we use a steganographic tools, any steganographic tools, like in this case, if we use the OpenStego. Okay? So basically we create a version of the malware using OpenStego, okay? And we put together these in sequence with the parameter weights, and then give it to Meta Defender to detect. And for example, if the malware is relatively small, it's not detected, but it's becoming to be big, there is a detection rate which is larger than 0. And this is in case we use the MaleficNet embedding, it's always 0, it's always not detected with the embedding assured. So standard antivirus cannot do that. As for statistical analysis, these are the comparison between the distribution of weights parameter of the baseline model, so the distribution of the parameter in the model without the malware, and the distribution of the model with the malware. You can see that they are overlapping. So the distribution is very, very similar. Also, we did some additional experiment using the Kolmogorov-Smirnov correlation, statistical correlation. And what turned out is that if you train the same model with the same data set, with different initialization, the distance of the distribution of the parameter is higher than the one we have here using the MaleficNet embedding. Okay. So it's very hard to detect just with statistical analysis because it's within a variation that you have naturally when you are training the model. Second, impact on model performance. Okay, this is again different malware, increasing size, and this is the accuracy that you get, the baseline and the malware embedding. So using Stuxnet, this is I think it's about 5 times bigger. This one, yes, please.
Regarding the stealthiness, what is the assumption about the downloads, the source of the download? Is the source...
What is the assumption about?
What is the assumption about this source from where people will download the model?
In place. There is no assumption. You can download whatever you want.
But the trustworthiness of the...
It's up to the user.
Okay, it's
It's up to the user.
because if the user trusts the source, it will not execute any analysis or they may
Yeah,
not
of course,
execute any
of course.
analysis.
That's, well, no, okay, I understand your point. This analysis is not from the point of view of the user. This analysis is only for the user to show that the attack is a devastating attack. So it is difficult to detect. Okay. Of course, if the user is downloading an application from Apple Store, he will trust the application and run it, regardless if it is a malware. He doesn't know.
Yeah.
We tried to do an agreement with Google to experiment this, but so far we didn't do any experiment. In C, probably we should see if this embedding is avoiding also the check that Google and Apple are doing on the app on the app before publishing. Yeah, so Stuxnet is about 160 kilobit, and Testover is about 5 times more. So this is big. And you see that here the accuracy is almost the same. Here there is some difference because this is bigger. In this case, for example, DenseNet. So if the network is small and the malware is higher, of course, it is affecting the performance. Right? So for example, DenseNet has 7 million. DenseNet has 7 million parameters. That's 7 million parameters, and here we have a size of about one megabit. So it's 1 bit every 7 parameters. Right? So this is affected. Right? But if you consider other case, for example, here you have, in this case you have more than 100 million parameters. So you see that the performance, the accuracy is the same. It's no difference in accuracy. Finally, robustness. So there are two kind of way to remove it. Canonical way. One is the fine tuning. So we train the network so it's going to overlap the signal. And the other one is parameter pruning. Where for parameter pruning, what we did, we put 0 in the parameter. So how many parameters you have to destroy, to remove before destroying the channel. So about the robustness, this is give you the ratio between the strength of the malware with respect to the noise of the parameter. Right? So how easy it is to recover the malware. Okay? Consider that if this value is higher than 1, it is possible to reconstruct 100% of the message. Okay, this is in communication theory. Here we are well above 1, we are about 7. And consider that this is the number of epochs that have been used to do the fine tuning. So after 60 epochs of fine tuning, still the signal is well above 7. and it keeps staying there. It doesn't go down. It keeps staying this way. Okay. So it is very hard to remove it with fine tuning. This is the kind of was used larger. It was first trained with C10 and then retrained with C1. So this 60 epoch of retraining with 61 and still with C100, still the signal of the malware was there. About the robustness with the parameter tuning, you know, if you put 25% of the parameter to 0, still the payload survive. And it starts not survive when you put 90% of the parameter to 0. Of course, if you have 90% of the parameter to 0, you are killing the model. The model is completely useless. If you kill the model, you can remove the model. That's it. That's the point. So, I think with that I can conclude. Okay, yeah. I don't know if you have a question. Pretty clear. Right? Now the detail, you can work out the details in the paper if you want to understand exactly how the embedding works. But then after working with it, I discovered that there can be other embedding, not only one. This is the major one, because the first one we had the sound theory, so we used it. But it's not the only one. If I have some time more, I would like to address another couple of problems, research problems, always related to machine learning and security. Yeah?
Please.
Quick. So that's that's better. This is a paper that we published recently. So this is called DOROS, which is an architecture for moving target defense. I don't know if anybody knows what is moving target defense. I just go fast. Moving target defense. This is the paper. Moving target defense is AAA, paradigm AAA. It's a new kind of defense. It's not relatively new. It has been studied at least since 5 to 10 years, but in particular by the US military. Because what they discovered is that they are spending a lot of money in classical defense, which is perimeter defense, like security defense. So you are defining perimeter of your network, and then you use the most sophisticated state-of-the-art devices, crypto and so on to defend your perimeter. And what they did is they discovered even spending billions and billions of dollars, and that's still they are doing. So this kind of medieval defense, they call it, in which you are you build walls, so it doesn't work. So they moved into this new kind of defense, which is based on annoyance. So basically, what you assume that the attacker is always in your territory. He's already there. So you are already attacked. When you build the system, attack is there. And it is a pretty good assumption today. Because today it's very easy to compromise from an attacker a computer inside the network. Because it's enough to send a phishing email to one of the weakest users. Now, the weakest user is the target. The user that you know that is not trained. So you can send this phishing email to the user is clicking this, and you have immediately a bot running the system that can be a remote to administration tools. It is installing a remote administration tool in the internal network. The attacker from outside can move in the network as it is inside. So all the billions of dollars that you are using to build your walls are useless. So you have to consider that the attacker is inside. If it is inside, you have what? Big tools that are doing annoyance. Annoyance means slowing down the attack. Because he's already inside. Slow down so that he can so that the defender has more time to somehow to detect the attack. Okay? The second A is attribution. So when you are doing this annoyance, you are collecting evidence to try to attribute the attack. Who is attacking you? Is a government? Is a private agency? Is a citizen? Is a student? Where is he? Right? Localize it. Right? So if you have time, if you slow down the attack, you have time also to do the attribution to collect the evidence. And these are the first two I is the one most used. The third one is attack. This is only for military. Okay? I mean, in the civil war you cannot do it. Because most of the time it happens that, for example, if a bank is attacked by somewhere outside, most of the time the attacker is the university. So the bank cannot attack the university. Because the university is only a bridge, right? It's only a step of the attack. It's not really the source of the attack. It's only somebody else that is using the computer of the university. Right? So this is not feasible in practice. It's only feasible in case of cyber war, but not in a non-civil war. But the first two are really relevant. Now they have different names. They call active defense. SANS, the institute, they have a document on this. They call it active defense, offensive countermeasure, cyber deception. Somehow they are related. They are all within the field of moving target defense. Now, why we are talking about that? This is theory, right? Now, theory is becoming practice. Now, we build a prototype of this, and this can be done because we have now a confluence of two major technologies. One is virtualization. So virtualization is a very mature technology. Thanks to all those ideas which have been developed for clouds, now it's very easy to virtualize systems. Very easy, efficient, can be efficient. The other thing is machine learning. So if I combine from the defense side, from the defense, now I'm talking only from the attacker point of view, from the defense point of view. If I combine virtualization and machine learning, I can create dynamic systems that keep changing in a way that is the most difficult for the attacker to attack. Okay, because I have kind of brain, which is the machine learning part, that is learning what the attacker is looking or what it wants to do, and is keep changing the configuration, the system, the version, the protocols, whatever it is in the network, so that it's going to slow down the attacker as much as possible. Okay, this is the major idea. Now, I don't want to go too much in the details because if you want, you can ask me. Anyway, the threat mode is inside, it's already there. These are the kind of, the objective of the attacker, not the scope. What he wants to do, since the attack is already there, like for example, he has compromised one node, what he wants to do? He wants to do privilege escalation. So now he's controlling my computer, for example, which is just a professor, so he has no right. He wants to become administrator of the network administrator. So he has to do privilege escalation. Another thing he has to do, of course, he wants to do information gathering. Another thing is lateral movement. That's important. So he's in one point of the network, and he wants to move in another point more critical, more sensitive to the network. In order to do that, he has to study the network, send packets around, gather information, and then decide what is his next node. And then keep doing that until he reaches the core of the network he's interested in. Now, the lateral movement is a part of the attack that requires human intervention from the attacker point of view. It's not something you can do automatic. Most part of the attack can be done automatic, but the lateral movement within the network is very sensitive. You need to be very careful not to be discovered, send as many packets as possible, send the packet only to where you know that there is a host, and so on. Very complex. So in this part, that moving target defense is very effective, because basically it is somehow defending in a phase where the human attacker has to be involved. And this is the weak point, right? Because it time consuming. Well, now, if you are doing, for example, a defense against port scanning, it's very hard because port scanning can be completely automatic, particularly machine learning can be extremely automatic. And so there is nothing you can do because you are not really slowing down the attack. Okay. To give you an idea what we do in Rome, basically is the idea is somehow related to Honeypot, right? What is the difference? Because now the classical approach to Honeypot where you have a production system here, and you have an Honeypot here. Then the attacker comes, the attacker goes to the Honeypot, right? But you know, the Honeypot has a big problem that should be realistic, should look realistic. This means that you need to have data that look realistic, users that look realistic. Like if you build an Honeypot and no one is using it, the attacker will discover it immediately. What they found, there are statistics from DARPA that on their system that basically a professional attacker discovered that the server is an Honeypot in less than a minute. In 1 minute, you know, okay, this is an Honeypot, so I go to someone else. Right? So what's happening in practice is that he logs to the Honeypot is collecting this information. Okay, we have an attacker, but the attacker is already moving to another one. Right? He starts checking for other systems. Same one, then he goes to others because he doesn't keep. So the advantage of the defense is very minimum, and the cost is very high because the Honeypot is very costly in terms to keep populating the Honeypot with information that's sensible, keeping the information up to date, and so on. So what instead we do with this with those, basically we have a production system that contains inside our agent. So basically it's like a production system contains the Honeypot inside. So when the attacker goes there, the production system starts behaving in a funny way because it keeps changing protocols, keeps changing ports. You can have a port open after a scan, and we do another scan. There are other ports, so not the same. So it behaves in a funny way. So the attacker at this point does. The attacker sees production system because every production system runs the defense system. It's like an antivirus. Every system has this. Doesn't make any difference. Now the point is that while the attacker interacts with the system is logging the activity, logs all the activity. And the attacker now has two choices. The first choice is still that the system is an Honeypot, and so goes somewhere else. So you have reached your goal of your system. The other thing is that he thinks, okay, this is a real system. In this case, he has to continue interacting, being detected, being logged, and also being delayed because it keeps changing the information you can get. Okay, that's the idea, and we build the prototype. I can show you probably through. This is basically the architecture. I have a demo, but probably not enough time. This is the architecture. You see the controller here, which is basically where the machine learning part is. And you have the pod. It's called pod because we use Docker engineer. So basically, you have in the same system there are the Docker component that are running the production system, and there is one component that runs your moving target defense tools in every node. And these tools are getting the message from whatever it comes in the system, communicating the controller. The controller can redeploy, change dynamically the configuration. Okay, this is the idea. Okay, these are some of the tools that are used by the defender, by the moving target defender. These are tools that are by everything is Linux based. These are common tools using Linux to forge, spoof, and change services, fake services, and so on. So these tools are coordinated by the controller to create an environment that is completely very hostile and keep changing to that point. Okay. Question?
What is the machine learning for in the controller?
The machine, oh, that's a good one. Okay. So the controller, initially, the controller was a set of human beings. So this was a kind of dashboard in which the system and network administrator were there, were looking. Okay? So when they were report, look, there is this node is under attack, they had tools like the one I show you, they have high-level tools in which they could change the configuration. Okay, this is the idea. This is the idea of the controller. Okay. Now we are introducing, we are integrating this machine learning tool that is doing the same. Okay. Yeah. Yes, doing it automatically.
The impact on the performance of each of the nodes is very minimal, right? Because of the virtualization capacity.
Exactly. Yes. Yeah.
So you couldn't do some kind of denial of service attack, like hopping from node to node and forcing the controller to communicate with every node, like very fast. It wouldn't be that. It wouldn't be that impactful on the system as a whole, I suppose.
Yeah, of course, on the system, in the production system, no. At the moment, maybe you can create a denial of service on the controller. Yeah.
Yeah, that's what I thought. Maybe you could hop from computer to computer, you know.
So to create a great amount of information.
So you overload the defense system.
Yeah, okay, this is a prototype. This is a prototype. But in general, you can handle this. Right? You can have, for example, cooperating control more than one controller, somehow partitioning the network, cooperating at the level, hierarchical controller, whatever.
Use the same balancing systems you use in every other
Exactly. So, yeah. So this is somehow logically centralized. It should not be physically centralized.
Yeah.
Okay. Yeah, I have. Well, I don't know how many minutes I have.
Sorry?
How
We we planned for an hour, but if
Well,
students are
it's
interested
1 hour.
and you are interested as well, I don't see why not.
How long does it
I don't know. I booked the room here for an hour, but there will be nothing probably.
Well, and just the last topic, which is something that is highlighted historically, which is this. G stands for history of computer science. It's part of history of computer science, for example. So this is about a paper that I published together with my author in 2013, 12 years ago. Okay, it was about hacking strategy. So basically, what we did, something that everybody now is doing, which is you have a model and you try to attack this model to find some information about the data set that we use to train that model. Okay, because if you have a data set, private data set with sensitive data, and I train a model with that, training a model doesn't mean encrypting the data. Right? So if you train the model, then looking at the model, somehow I can do some inversion and try to find out the property of that. This is what we did. In 2000, we did it before. I think this is the first time we published this on archive, 2013, but we submitted before. It was rejected. This was rejected. We submitted in 2012 to CCS 2012. You know, this is a famous conference. It's one of the top conference flagship in computer security. It's called Computer and Communication, ACI Computer 2000. They rejected because they were saying, why do you believe the statistical information about the distribution of training data is a real privacy problem? They say, okay, this is not a problem. Why are you doing this? What is the problem? They say, perhaps can be of interest for the machine learning community, but not security. So if you want, just submit to NIPS. Now, NIPS is a conference on neural information processing system. I don't know if you know. It's the major conference on machine learning. So they will say, okay, it's not good for security, send it to me. This was terrible, right? We keep submitting it to other conference, top conference, so it was always rejected. And then in 2015, since some of these students that were teachers who did the degree, we submitted this to a second tier journal. It was published. It's a bad story, right? What's happened worse than that? That similar techniques like model inversion attack was published in 2015 in CCS, same conference, 3 years later, they published it. No acknowledgement to our work. They ignore it. Then in 2016, there was a steering machine learning model prediction API. They were always using the same technique we were using, no acknowledgement. Completely ignoring. Then, finally, in 2018, there was this work published on CCS, by the way, 2018. So 6 years later, and they were doing probability inference attack, exactly the same we were doing, but they mentioned our paper. And okay, there was some guy in Italy that did this in 2012, but 2015, but we are doing better. They were improving the technique, of course, the technique keep improving. And this was one of the first papers that published that was citing our paper. So it was 2018, 5 years later. Right, 5 years later. Then, okay, this is not important. Then, it is because I'm telling it today, there was this, well, in the meantime, in this, from 2018 to now, there was some people citing our paper. Some Bibles citing our paper, because it's difficult to find. Right? Then there was this, this document that was published now on adversarial machine learning, taxonomy terminology. This document was published in March 2025. this map. Okay? And if you look at the chapter probability inference, they say probability inference attack were introduced by Ortega. So, and so this is a good ending because this document is becoming like fundamental standard to say what is the and there is a key lesson here, in particular for students. It is my key lesson. So perseverance is essential. So if you think you have a good idea, you have to keep going with it. When you have an idea, time matters. So if you need to have an idea, when is time mature for that idea? Our idea was too early. No, it was 10 years early. It was too early. We had to wait a bit to publish. But one of the major problems is this: don't be afraid to submit. So because what's happened to us that when we submitted for 3 years to the major company that was rejected, we stopped submitting and we decided to go for a second final jury. And probably we should have continuously submitted to that. Okay, that's it. So if you want to have more details about that, I can tell you.
Yeah.
Right, I have another one, another topic that I should again, that's 2 minutes, but this is important, about password guessing. Password guessing in machine learning. Anybody? I have to show this because this is something that can give you idea. I think it should be here. It should be in this paper. It should be somewhere here. I should have this line. I have this. Should have something. Okay. Yeah. 2 words about password. So you know the problem with password, right? So people use easy password and you may have to make it harder and so on. What we did with this work, we did the following. The human being have a way to create password, even difficult password. It is typical of the human brain. It's not machine-based, it's the way human brain works. How we can discover it? How we can discover it? How humans create password. Difficult password. Not so easy, right? We use an empirical way to do this. So what we did, we took a leaked password that are published on the internet. There are many, huge password, gigabytes of password. And we train a machine learning model with those passwords. So we say the machine learning model, look at this password and try to find out the distribution, the correlation among these passwords. And machine learning models are very good. Okay? Once you do that, once you have done that, what you need, you can start generating passwords that are in a subset of the all possible passwords, which is the subset that human being is going to use, right? Because that correlate to what human think, and we call it, and we discovered it is very efficient way to create password. Okay, so there are several papers on this now. So the first paper was a few years ago. Now others publish this paper. The first paper is called Pascal because he used generative adversarial network to correlate the password. Well, this is the kind of, for example, this is the kind of password you can generate. These are computer generated passwords, right? They look like passwords that humans could have generated. And this paper had a lot of impact also on newspapers. No, they say, okay, this is the end of password. Don't use it on password. And this is indeed the end of password because as machine learning is going to be more efficient, this password guessing technique will be even more efficient. I have some statistics, but not on the slides. But anyway, compared with the classical rule-based password cracking, this is much more efficient. 100 times more efficient. Okay, I think with that, thank you for your attention.
I want to wrap it up saying that it's very likely that we start collaborating much more between Luigi and La Sapienza, especially in this security part. Okay, very likely in June I'll be there in Italy paying a visit, and then if students are interested in these kind of projects, I can serve as a bridge between you and Luigi. Okay. So thank you all for coming. Thank you.
Yes, pleasure. The one about password.